Hey, good afternoon, everyone. I hope you are doing all right and ready to learn some physics. Are you? I'm sure you are. Okay. So we learn about charges and then we learn about forces between charges and how to calculate the force using Coulomb's law, right? Now we're going to talk about field. So it is basically force on a unit charge. Okay, just like if we have, let's say, a packet of 5 pound apple, and if that costs $10, then how much does a pound of apple cost? And that turns out to be handy if you are comparing, let's say, different kind of apple of different size with different prices, right? If you are, let's say, comparing one kind of apple with another kind, you want to know, what's the price per pound is. And that way you can tell, okay, which one has more value and so on. Okay. Same thing goes here with the pill. Okay. So what we are doing is basically we are looking at force per unit charge. So just like when we say, okay, we have a force per unit, I mean, price per unit pound or price per pound, that means we don't have to worry about like how big the package is, how small the package is. All we have to do is once we know how big the package is, we just multiply with the price per pound. Same thing. We can find the force by just multiplying by the field. Okay, once we have the field. So this is the equation for field, and uppercase E is the notation for the field, electric field. And remember, this is nothing different than the gravitational field. Okay. And we talked about gravitational force can be written as m times g. And this gravitational field strength is the lowercase g, although we said, okay, it was acceleration due to gravity, but later in the force of gravity chapter, we introduced this as a force per unit mass, okay? Force on 1 kilogram mass. Similarly, force on unit charge here is the field. So to experience force, we have to have two masses, but field is already there. Same thing goes here in case of electric field as well. So we can have field as long as we have a source charge, a charge. Could be any charge, right? As long as we have a charge, that charge produces field all around it. Field is already there, okay? Now, if you bring this charge, let's say Q over here, then there gonna be force between these two charges. So that's the relationship between force, field, and the charge. Okay, mathematically, it is just the force per unit charge. Okay, and I think that's what I have written here. And I think we talked about this last class as well at the end. But I'm just picking up from here because we're going to be mostly talking about field today and field lines. So here we can go from this equation to this equation. How? We know if we can use Coulomb's law equation for the force between two charges. Here, two charges are, let's say, big charge, let's say source charge, and little charge, let's say test charge, just a notation, okay? And then R square. So now when we divide this by Q, a charge, then we need to divide this side by that charge as well, and we can cancel that charge. So we get this equation. Okay, so F over Q is the electric field we defined. Okay, so electric field can be written in terms of this or that, depending on what we know and what we want. And similarly, now force on a charge can be written as Q times E. Okay. So if you know electric field at any point, and then you can find the force on any charge just simply by multiplying that charge by the field. That's it. Okay. So now here is a question for you then. Okay. So this idea is similar to what we learned in terms of, like force. The idea is same. For force, we have to have charge at the point, but for the field, we don't need charge. So even if charge is not there, I mean, test charge, source charge has to be there. So for example, in case of force example, we may have, let's say Q here to Q here, something like that, maybe here, something like that. That would be the question, right? Same question can be force or field, okay? But here, if we are writing in terms of force, then you have to have charge here on those point of interest. But if we are talking about field, then we don't need this charge, okay? I mean, we don't need charge at this point. So what that means, now you can figure out the field just like you would, because direction of field and force, they are same. So the field is F over Q. So that means whatever direction of force is, so is the direction of field on that point, okay? So this Q test charge we call is always assumed to be positive. So for example, if I am looking at force at this point, sorry, field at this point due to this charge and this charge, what should I be looking at? I'll show you one example here and then you can do all of these. So basically, let's say because of the positive charge, let's write that as a E and put the positive, let's say, subscript. So this is positive charge. So here the field gonna be pointing away because of that. Okay. So we call that due to positive. Now negative is gonna be pulling. And since this is closer, it's gonna pull it harder. So that's why I'm drawing longer arrow here. Okay. So we have these two field. So that means net field in this case gonna be, of course, in this direction, since this is larger than this one. And how do I know that? Because this point is farther from the positive charge, R is larger, and since R is in denominator in our field equation, larger the R, smaller the field, just like force, okay? But over here, this is closer. R for this negative charge and this point. So the distance between these two are smaller, means the force gonna be, or the, I should say, field gonna be larger. Okay. So that's how you want to look at each of those dots and see. So this small charge here is like a test charge, okay? Oh, looks like, let's make this force now field, okay? So I slightly modified this, okay? Let's look at field. And now I'm opening the poll. Okay, 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see how did we do here. So we have all of them, but C is a little more. So I'll just keep doing what I did here, right? So in this case, this is going to be pointing this way, and distance here is R. And for this one, what happens? Negative charge is attracting in the same direction. So basically E positive and E negative, they are pointing in the same direction. And distance between point and the charges, they are same for both of these, are here, and so is over here. So that means they have equal field. Both of them are pointing in the same direction. These were not equal, but they are pointing in opposite direction. And over here, let's see what happens. See, positive, right? So now what happens is positive, this one is closer. So this is going to push it a bit harder. And this one is a bit farther, but it's still going to be pushing. So that means it's going to be pushing but a bit lower. Okay. So that's that. And how about here? So this is going to pull towards this, and this also going to pull towards it. So that means in this case, the net is 0 here. Okay. And over here, both of these are in same direction. And over here, both of these are in same direction. So A and C, they are the, larger possibilities. But in this case, what happens is in C, what happens? The one is larger than the other. So for example, force due to this one, just this one, is same as force due to this one at this point. But force due to this one is way smaller because it is twice distance. But in this case, what do you see? The distances are same, so they are equal force and large force, smaller distance, larger force. So it looks like A gonna have the larger force or the field, in this case, field and force, they're gonna be proportional here, okay? We are talking about just tiny charge here. So looks like A gonna be the correct answer in this case. So quite a few also chose C. I guess both positive, so they pushes harder, you thought. But remember, here, this is pushing, but this is pulling at the same time, and they have the equal values because they are closer. They are at equal distance from the point. But over here, although both of these are acting in the same direction, one is larger than the another one. And the larger one in this case is equal to one of these here. Means this one definitely gonna be larger. Okay. So if just my pen is not working. Okay. So for example, let's say in this case, if this was 10 and this was 10, then in this case, because of this, it would be 10. But now distance is double. So it would be just quarter due to this. That means it's going to be 2.5, let's say. Okay. Because distance double means field going to be just quarter. Because field depends on distance squared. I should write this. KQ R squared. Okay. So double distance, and you square that, you have 4 times R squared. So that means 4 in denominator means it's only quarter. So that's why this is bigger than that one. And in this case, force and field, they're going to be equivalent because it's acting on the same positive charge. Okay. They're not going to be same in terms of value, but they're going to be proportional. So largest field here, largest force here as well. Okay. So did I choose answer? Yes. So anything you like to add or ask on this one?
If you could explain why it's A again instead of C, that would be great.
Okay, so here at this point, both of these forces are acting in the same direction. Okay, positive. So see, this is a small positive charge, and that's what we assume when we define field. Okay, the test charge is small positive charge. So this positive, and there is, let's say, it's pushing that away because, similar charge they repel. So that means we can say, okay, that is 10. And now this one is negative. So it's going to attract the positive charge. So that means it's also going to be pointing same way. And since this distance is same as this distance, and by the way, the charges, they have same magnitude, right? So whatever the value of the force field is over there, it's going to be same. So I'm just putting a number here. So it becomes 10 plus 10, 20, for example. Now, if we look at this point over here, what happens? It's pushing this way, and this distance is same as this distance, means the force, field going to be same, 10, let's say. But this one is at double distance, so that means it's going to be only quarter. So that means quarter of 10 is 2.5. So if I add total 12.5, here total 20. Others even smaller if you do the same thing, okay? So for example, here this is 10 and this is going to be 2.5. So the total going to be 7.5 in this direction, okay? I don't know if I should be writing like that. So in that direction, that, and over here, I already said it's going to be 0 because this 10 and 10 going to be pointing in opposite direction. Yeah, it is a vector sum. That's what I'm adding. That's right. So there is direct message. So when you write this kind of message, maybe you want to choose to everyone so that others can also look at your message and they will know what I'm talking about, right? So the message is, could you also determine the answer is A by assuming their vector sum? And that's what I'm doing. So number introduction gives you vector, right? And that's what I'm doing. Okay. Yeah, thank you for putting that question on the public as well. So here the idea of, like there is a source charge and we usually denote that by uppercase Q. And there is this small positive charge, we call that test charge. So the field is the force on that test charge at that point. If this test charge is closer, force is going to be larger. When test charge is farther, it's going to be smaller, and so on. So if I were to map that, this is how it looks like. Okay. So farther you are, they get smaller, right? And closer you are, they are larger. But there in all direction, it is actually 3D, okay, map. So three-dimensional rather than just two-dimension, but in our screen, it is basically two-dimension, right? So we looked at this picture last time as well. We said, okay, similar kind of charges, they are repelling each other. And because of that, the hair of this kid is, right, rising like that. Or we can also say, okay, once we have this charge, what happens? There is this field and they are experiencing something like that. And this field map looks like the map of this hair as well. Okay. And there is this animation on the PET, PHET. Where did it go? So over here you can put some charge, positive charge in the field. That's how it looks like. If you start from here, that's how it's going to look like. If you start from here, that's how it's going to look like. That's for positive charge. So they are all pointing away because direction of force and field are same. And when we are describing field, we are saying, okay, it is force on tiny positive charge. So positive charge repels means uh, any positive charge is going to experience force radially away. Okay. Now, if I, let's say, put negative charge over here, what's going to happen? So that's how the field line looks like, and that's what we call dipole. Okay. Positive and negative charge separated by a certain distance, and positive and negative charge, they have same value. Okay. So now there is this, let's say, sensor. Now what happens? When there is only one, then the effect gonna be just from one. But when we have two, for example, like this, see here, just like we had the question, right, in our PowerPoint previous question. See, when it is exactly at the middle, it becomes kind of larger. But if it is on the it's kind of hard to tell that. See how it is pointing something like that. So these tiny arrows, they are basically giving us the direction of field at that point. Okay, the field is pointing in that direction. So that's the direction of field. So if we were to connect these lines, that's going to give us the, let's see, what does it show here? So if we were to connect these with a continuous line, that's what we call field lines. So feel free to go and play with this one, okay? And there is this voltmeter as well that gives you a reading, okay? When you are close to the positive side, you get positive voltage. When you are more towards the negative, you get negative, but when you are dead center, at the dead center, it's going to be 0, just like in between two, right? It's not supposed to be 0 here. So yes, it's more kind of negative on this side. When you go more positive, okay? So you can play and learn from there. Now, so now the field line gonna depend on what kind of source we have. And there is a source, short video that shows us, like how the field line looks like for different charge configuration. So this video is in my screen. I'm hoping you are looking at that, right? And So we have these two wires. You see one side is dipping one kind of wire here, another wire here, and it is connected to this red wire here. That means it has a positive charge here, okay? This wire has a lot of positive charge. Let's think something like that. And this wire has a negative charge, okay? Now, what they do is they basically spread a tiny particle of the color. I think it's potassium permanganate that makes the dye. I think they name it here. See how they shape just like we saw. Oops. So you can see how they are like, okay, the one that goes straight, more like a straight, and then bit curved, and then more and more curved as we go farther. Okay, just like we saw in that animation. So now, if so, this is, you can think of this as a point charge here. One wire is a point charge, a negative charge, and this as a positive charge. And of course, you don't see the arrow over here. Okay, so arrow, we need to just remember how the arrow works. And now what we have is this. This one is this, let's say a little metal rod kind of thingy here that is connected to the negative wire that you cannot see. But over here you see the positive. Now let's take a look. How does it look? The one that goes from the middle, that is good, they go straight. But one that starts here, kind of they go curved like that. See that? So basically, if we leave or release a positive charge somewhere in between, it experiences force because of these two kinds of charges. And which way it's going to move going to depend on the net force or the net field at that point, okay? And that's how the trajectory of that positive charge going to look like. That's how a positive charge is going to move, okay? So for example, when I leave it here, so most of the force is coming from this red wire connected, let's say, electrode. And because of that, it starts moving radially away. But now it's also experiencing some force from this. But that force is smaller compared to this force because when the charge is over here, it is very close to this positive charge. So it experiences more force or the field because of that positive charge. But once it reaches, let's say, somewhere in between where the distance are equal, then these both forces are kind of equal. So that's why they are kind of moving in a straight line like that. And then once they go close, now more force coming from this rod means they're going to just experiencing more force from the rod and tiny force from this, positively charged, let's say, this pole. And because of that, what happens? They just go straight. So if you pay attention that all these lines are landing perpendicular, okay? All of them, no matter where they are landing from, they are all landing perpendicular, okay? So I'll show you other sketch that, I have made for the note as well. But this is kind of, this is kind of cool because you can see actually what's going on. Now here, what do you see? The positive terminal is at the center and this whole outer circle is negative. So what happens in this case? They just go radially outward. Okay, they just go radially outward. Now we have both metal, rod or plate kind of situation. Oh, I think it's going really fast. So let me get back a little bit here. So you see these lines are basically straight line. And that's what we call, infinitely long charged rod. And we'll also call them, we can call them capacitors, okay? They can store charge and field inside. So now, again, looks like it's basically repeating or showing the same thing here we saw. Okay. So it's just showing how they did it, okay? How they are setting up. So now let's look at a bit clear picture that if we have a positive charge, then the field line, they are just radially going out, because if you release a positive charge somewhere around here, right? Around here, it's going to just move straight away. If you release here, it's going to move radially away. If you release here, it's going to move radially away. But if you have the source charge negative, if you release a positive charge, it's going to rush towards that negative charge. So that's why these field lines are getting inside that, ending at that negative charge. Okay. And just like we saw, if we have two charges and they are equal, see the positive Q and negative Q, so that means the values are equal. So this kind of uh, setup is also called dipole. Like this is one pole, this is another pole. So both poles, dipole, for example, right? So here at the middle, they go straight and they start from positive charge and go like that, right? And here, let's say this is double in terms of value compared to this. Okay. So that means there are twice as many lines coming out compared to this one here because of charge being double. So density of line coming out more means field is stronger. Larger the value of charge, stronger the field. So wherever we see this dense line, that's where the stronger the field is. Okay, denser the lines, stronger the field. And if we have, for example, similar kind of charge, then what happens here? Right, at this point, field is zero. Why? Because this one is pushing this way, and this one is pushing this way, and they are at equal distance. So that means the value is exactly same. So that's why the direction being opposite, one positive, another negative, makes it zero. Net is zero. Okay, so that's how the field is zero if you have charges like that. Okay, so there's going to be a line exactly at the middle where the field is going to be exactly zero, but anywhere else it's not going to be exactly zero. Okay. So these are the properties I was also talking about when I was showing you those, right? So they start at the positive and they end right there on the negative. Okay, so that's how this looks like. Okay. And direction of electric field at any point on the line. For example, let's say if I want to find direction of electric field at that point, what I have to do, I need to draw a tangent line. Okay, so I do put another point right next to it and then draw something like that. Over here, it's going to be like that. So it's tangent. Okay, it's a tangent. Over here like that, over here, that's like that. So that's what it is showing. So how do you find field from field lines? At that point, you draw a tangent line, okay, on the field line, and that tangent line represents the direction of field at that point. And I already said this density, denser it is, the stronger the field. So for example, if I look at here versus here, what happens? If I were to make same size circle, let's say, then only one line is passing through this point over here. But at point B, there are three lines are passing for the same size circle, okay? So that means it is 3 times more dense. And that makes sense because it is closer to the charge. Closer to the charge, higher the field. We can tell that too. But even if charge is not there and you are given field line, for example, let's say this picture, I don't show you this, right? And then I give you 2 points, let's say over here versus over there, A and B, and ask where is the field stronger? Then you can tell field is stronger here because the lines, separation of line between these two lines, the separation is smaller compared to this one over here, right? So we can say in this region, field is smaller compared to over here. Over here, even is smaller. Over here, even is smaller. Even is smaller, okay? Because less dense the line gets. And another important property is this line cannot intersect each other. So for example, if they were to intersect somehow, let's say there is one coming out and intersecting like that, that means if I were to draw a tangent line at this one, that tangent line gonna tell me, okay, field is pointing this way. But tangent line over here tells me field is pointing that way. Which one is correct? Both cannot be correct. Field cannot be in two different direction at a particular point. At a particular point, net field is always one in a particular direction. Okay, and so that's why they cannot intersect, and they don't. As you can see, so many lines, we drew here, and even in the previous slides here, although there were so many of coming out, they were not intersecting, they're not crossing each other. Okay, neither there nor there, right? So that is another property. Okay, so now looks like, oh, is that all? Looks like that's supposed to be the full question. Okay. So now, what do you think is the direction of electric field at that point? So A, B, C, D, E, all those are choices. That E is not the electric field here, rather it's just a choice, okay? And so what do you think? Okay, let's do 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we got all of them. But the correct answer is C in this case, just like we just discussed. What happens at this point, you draw a tangent line, and tangent line gonna look like that. So here is another slide, which I'm actually calculating the value. So this kind of setup is called dipole, right? So yes, in our previous question, we had charge sitting along the horizontal line. Now they are sitting along the vertical line. And see how the field line points more towards the negative charge rather than pointing this way. It's pointing that way. Okay. So how do we get that? So let's take a look here. Okay. This one I just copied from my note. Okay. So this drawing again, this one would be a little bit, uh, uh, time consuming. So now what you want to do is you want to look at the field due to a charge at a time at this point. So we want to find net field due to these two charges, okay? And this point is at equal distance from this positive charge and the negative charge. So that's what it is there, okay? So now, let's just look at the field due to the positive charge at this point first. Tune out everything, okay? Just one. Field due to this positive Q charge at this point, okay? So now, field, direction of field is as if the force on the positive charge at that point. So that means this positive charge gets repelled by this positive here. So although there is no positive charge, we assume there is positive charge to determine the direction. That's a convention, right? So it's pointing away because that is saying, okay, go away from me, okay? Positive charge to the positive charge, it says it repels, means say go away. Now, that is one. So what we can do is, okay, we can assume, okay, there is a horizontal x-axis, vertical y-axis, and we can write its component, okay? So if we say, okay, this angle is theta, then this is going to be cosine component of this one, okay? Because this is going to be the adjacent, right? So we come here and come here. So this is going to be adjacent to that angle, and this is going to be opposite. So opposite means it's going to be sine, but rather than drawing here, we draw from that point here, and that's what we are doing. So the red arrow here represents that. Now, that is the field due to positive charge, right? This E plus is the field due to positive charge, and this E plus cosine theta and E plus sine theta are the components. It's components. So why am I doing components? Because this one is neither along the x-axis nor along the y-axis. When you have this kind of situation, you need to write in terms of components so that we can do the further math. Okay. So now let's tune out all the reds and let's just focus on blue. So now we are looking at field due to negative charge at this point. So at this point, we assume when we are trying to figure out direction of field, we assume there is tiny positive charge. So that means that positive charge gets attracted. So that's why you see this electric field here. And by the way, this E negative does not mean that's a negative electric field. It simply means this is just a notation. This is the field due to negative charge. And same thing goes with this E with the positive sign. It's a field due to positive sign. Okay, that's it. And then now what happens? Just like we did here, we can find the component of this field due to negative charge. This way would be adjacent to this angle. And by the way, with geometry, we can tell this angle and this angle going to be same. So this is going to be the cosine component because this side is adjacent and this side is opposite, means this is going to be sine component. And that's what, oops, that is not red, rather this one is there. So now, what is total field due to these two? See here, this one and that one. The E, negative or positive, because that point is at exactly same distance from both positive and negative charge. What happens? This E positive or E negative, both of them have exactly same value. Why? The value of charge is same and distance is same. So that means these are same. The values are same. And if we look at the X component, these two, they have same value, but they are pointing in opposite direction. So that means they cancel after we do vector sum or the net becomes 0. So the contribution to the total or net field because of the X components or horizontal component in this case, it's a 0, no contribution. They are just balancing each other, canceling each other, okay? But on the vertical side, both of them are pointing in the same direction. So that means they're going to add up. So what is net? Then that's going to be the sum of that positive and negative, and the sign component from each of those survives. So that means we can add them. So it's like saying, okay, that is E plus, and due to negative, the field is still, the value is still same. And if we, and since they are pointing in the same direction, we can add them. So this is k cube, this is k cube, r square, r square. So same thing, when we add both of them, it just becomes 2k cube over r square. When we add that e positive and the e subs negative. Okay, so that's that. And there is theta, sine theta, there is sine theta. So that's why the sine theta, because we are adding the components. Okay, and it's pointing down in this case. Okay, on the screen. So that is the net field due to this. And you can see it's pointing parallel. I mean, pointing this, since this point is exactly at the middle, what happens is it's pointing like a parallel to the line joining to this. If we go back and look at previous slide I had, here, it's the same thing. See, it's pointing going that way, and it's pointing towards the negative side, but it is parallel to the lining joining them. And that is the case only at exactly at the middle over there. Okay, if it was on the side, then this wouldn't be pointing this way, rather it would be tangent like that. Okay, so that's how it works. You need to draw a tangent line, and here we just did the analysis to figure out indeed that's the case. Now if we look at this geometry, we can replace this sine theta, for example, by this geometry here. So if I think I kind of made typo over here. So let's see how does the sine theta looks like. So this is theta, right? Theta is right there. So R, this is going to be very, so these are very close. So for example, let's say if we are looking at dipole nature of water molecule, one oxygen and another oxygen of water, how far they are? They are in micrometer scale. They are very close, okay? So that's why, although in this diagram it may look like, hey, they are very far, in practice, what happens is these charges are very close to each other. So this distance is very small, so that means this R, and that R, they are very close. For example, when these 2 points are same and I have this, so all these lines are going to have same length, approximately, okay? So that's why I'm writing R even for this one there. So now what happens here? Sine theta is opposite over, what is sine theta? Opposite over hypotenuse, right? So in this case, opposite gonna be this d over 2, and hypotenuse gonna be r, okay? So sine theta is opposite over hypotenuse, and opposite in this case is d over 2, and hypotenuse is r, so that gives you d over 2r. So that's why we can replace this sine theta by that. So when we do that, we have the net electric field. Okay, we don't need to measure the angle. All we need to do is know the charge and know the distance between the positive and negative charges, right, in the dipole, and how far the point of interest is. Okay, so that way we can figure out the electric field due to dipole at a point. So finding the net field at this point is the easiest one. This point is easiest. Here, probably you can guess that's going to be, looks like, easier as well, because both of them are pointing in the same direction. but any other points, you're gonna have, do the same thing with a more component, but the value is gonna be different at those points. So we'll just keep it here. So notice that this thing, this dipole, I mean, I should say field due to dipole at that point points towards the, negative charge rather than going that way, it's going that way. So that's what I mean when I say it's pointing towards, negative charge. If I look at here, it's going to be pointing that way as well. Okay. If I look at here, it's going to be pointing that way, assuming this is exactly at the same distance. But if it is there, this is going to be pointing more like that rather than this, okay? It's the net field, so sum of two fields, okay? So we need to draw and then add them using the vector addition method, okay? Okay, so here is a question for you. And you have 1 minute and 30 seconds to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how we got and what we got. So looks like B and D more popular. D is most popular, and that is correct answer. So that is one of the property, okay, of they never cross. That's what we talked about, one of the property, right? If they were to cross, then that would mean there would be field pointing into different direction at the same point. So basically, that question is checking your knowledge of this property. Okay. Ooh, what happened here? I think that's supposed to be epsilon naught. Maybe it's a good time to take break. So let's take break and we'll just pick it up from here. So if I had to choose one, I would choose D, but B is also equally valid. Okay. So what I'm going to do is I'm going to say, okay, B is also good choice. So now, two equally charged plates separated by a distance D, and each plate has area A. So What happens if I were to draw field lines in this kind of setup? What's going to happen? Just like we saw the demo in this demo video, and over here, if we do that, it's going to be go from positive towards negative, right? So that's how they're gonna look like. So in 2 dimension, that's how they look like. Okay. So that's how the field line looks like. Over here, what's nice thing about this field line is that their density is equal. Means electric field is same throughout in between these plates. So this is one charged plate and charge is negative. This is another charged plate and charge is positive. And when we draw a field, what happens? Remember, equation of field of a point charge is this. So when you have just a point charge, then field is this. So it tells us, okay, field depends on the distance. But when we have this kind of charge distribution, see, this is not just a point charge, but charges that are, like let's say stretched on a line like this. And if we look at the field between these two oppositely charged lines or the metals, what happens? We get this field and their density is uniform. That means the field is uniform. Other way around, field is constant. Okay, field is constant. So now in that case, then how do we write the electric field in that kind of situation? We look at field when we have dipole, right? In a special point like that, right? What if we have this line of charges? What's the field? What's the value of field? And for that, the formula for that field, where I'm not deriving it, is given by this equation. Here, this thing is epsilon naught. Remember K we had in the force equation or the field equation, right? Basically, this K is the convenient notation of 1 over 4 pi epsilon naught. And this K, not K, but epsilon naught is the fundamental constant. We are writing like this to make it look like a gravitational force, similar to gravitational force. But actually, I should say in this case, field, actually, it's supposed to be written somewhere, something like this, okay? So we are replacing this 1 over 4 pi epsilon naught by this K notation, okay? And this is called electric permittivity of free space, okay? It's epsilon naught, and this is the fundamental one, okay? So whenever we like, we can also write this equation as 4 pi epsilon naught and then r square over here, okay? So this being the field of a point charge, it is a distance dependent. But in this special kind of setup, turns out field in the middle does not depend on the distance from the charge, okay? So that's what it is saying. And this Q over A, so Q is amount of charge in one of the plate, and both of these plates have same amount of charge. Only difference is one has positive kind of charge, another one has a negative kind of charge. And this A is area of such plate. So this Q over A, we call that surface density, okay? Surface charge density. Again, this PowerPoint messed up with that font, okay? So this notation, we call that sigma, lowercase sigma. Probably you are familiar with summation sign. This is also sigma, but this is uppercase sigma, and this is lowercase sigma. And this is just a notation for Q over A. Oh, looks like I did not write that. Sigma is Q over A. I think I indicated that by just drawing this dash line here, okay? And I wrote this, what I wrote here. Yeah, sorry about this notation messed up. So what did we learn here? Field between two long charged plate, oppositely charged plate, is constant, and its value is given by this equation here, okay? Either this or just this one here, okay? And this kind of field is called constant field or uniform field, okay? Uniform also means constant, not changing, okay? Now with that, here is a question. So let's just focus on this one here. So what do you think? You have 30 seconds to answer this. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. So mostly yes. Oh, that's interesting. The correct answer is no. Uniform means constant, means it's not changing, okay? If you look at here versus here, see the line is more dense here compared to that. So that means field E is stronger here. Over here, weaker. So field is changing, not constant, means not uniform, okay? Looks so nice, uniform from this sketch, right? But that's not uniform. See the uniform, how did it look? Everywhere the field density was same, okay? It wasn't changing in between. But over here, they're changing. If we look at this area, everywhere they are different, okay? Changing means not uniform or non-uniform. So this is uniform field. Now, if we have a positive charge, that's how it moves, right? So if I release this charge from here, it's going to move in the direction of electric field. Or you can just look at it's positive charge here, negative charge here. Positive is pushing, negative is pulling. So that means it's going to go that way, right? But negative charge, See, this negative gets pushed by negative charge and pulled by positive charge. So that's why this negative charge is going to be moving towards the positive plate, right? So in terms of field, what do you see? Positive charge moves in the direction of field. And that is the definition of the direction of field, actually. And negative moves opposite to the field. So over here, these charges are shown, so we can just tell just by looking at this. But if you are just given, let's say, a field line and like that, there is no positive or negative charges shown. And if you are asked what this positive charge is gonna do in this field, then you should be able to tell, okay, it's gonna just follow the field lines, okay? Well, how about negative charge? It's gonna move in the opposite direction of field. So it's negative charge swims in the opposite direction of current, like a fish, salmon, right? And the positive charge swims like me. If I get into the, let's say the water, river where there is water flowing, I cannot swim against the current. I just go flow with the current, okay? So positive charge does that, but negative goes opposite to the field. Okay, so and that's what you want to keep in mind. Okay, so now when we put charge in a field, what happens? It experiences force, and it came basically from the definition of field. Okay, so we know that. So that means it experiences force means it's going to have acceleration. See, field is constant, means acceleration going to be constant. Okay, field is constant means acceleration going to be constant. So acceleration constant does not mean velocity is not changing. Velocity is changing, but velocity is changing at constant rate. Okay. So for per second, if it is going from 2 to 4, the change is by 2, 2 to 4, difference is 2, right? Now second, if it goes from 4 to 6, the difference is still 2. So that kind of change is constant, we say. So the acceleration is constant when that happens. So if the speed is increasing like 0, 2, 4, 6, 8, and then that is called constant acceleration. Okay. So constant acceleration means velocity is changing at that rate, whatever the acceleration is. And we can find the acceleration by using Newton's second law, assuming that there is just one force acting. So I'm not writing sum of force here because I'm saying, okay, that's my net force. Okay, let's say that's my net force. And that is equal to Q times E for the charge. Okay, so that's that. So now see how we had in physics 1, we had this, or F is ma kind of thing, right? So now, what is F? F is not mg. Sometimes when we had gravitational force, we replaced F by mg. But now we have electric force. So that means we have to replace F by, or the force by, charge times the field. That's it. So this is constant acceleration, means it's going to follow the kinematic equation. Oh, that physics 1 all over again, right? Hopefully you recognize these equations, okay? So final velocity is equal to initial velocity plus acceleration times time interval. And these are vectors, so final velocity in a particular direction is equal to the initial velocity in that direction plus acceleration in that direction times time interval. That's how you want to read. So that's why we may also write by putting subscript extra subscript saying, okay, all they are pointing in the same direction. It could be in the x direction or could be in y direction. Okay. So that's how we can use. Now we have kinematic equation. So that means you can describe motion just like you would for any object that you learn in physics 1. Only difference is that now the acceleration is found by doing this, QE over M. Okay, acceleration depends on charge and the electric field. That's it. Only that's the difference. Only that's the new thing. Everything gonna be same. So now here is this question. Okay, so this is positive charge and this is field, and this positive charge is moving. Okay, so it's not at rest, rather it's already moving with velocity v. So now you waited for very short time, let's say 10th of a second or even less. Okay, how would the velocity direction gonna look like? And there are choices. Okay, go ahead, choose one. And you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see, how did we do here? We have B and C. B and C mostly, but we also have A, we have E, we have D, but majority came B and C. What's the difference between B and C? More tilted. This one is more angled compared to that one. So angle is large. So that means it has turned a little bit more than this one. So yeah, both of these are possible answer, but since this says very short time later, so that means it does not get chance to turn a lot, just a little bit. Okay, so that's why I think C is the best choice in this case. So why is turning? See, the field is acting in that direction, and we learned that positive charge moves in the direction of field. Oh, then why A is not the correct answer? A would be correct answer if it wasn't moving already, but since it's already moving, and once we apply field, what happens? The result gonna be like a vector sum of those, so somewhere in between. Okay, in short time, it's gonna be just tilted a little bit. Longer you wait, becomes more tilted, and then eventually this is gonna be A. Okay, eventually after a long time. So it looks like C is the best choice in this case because it said very short time. There is one question similar to that one. So what do you think? And again, you have total 1 minute for this. Proton means positive charge. Proton has a positive charge. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Follows the path between the field, that's majority. See, it can never cross the flow. Okay, so remember, field line is basically representation of a path a positive charge would move. Okay, if we were to cross, that means it violates that non-crossing law. Okay, so it's going to just follow the stream. Okay, so that's what it's going to do. Oh, I'm just noticing there was a question on the chat, Zoom chat. It will be A after it comes to rest. It may, be A even before it comes to the rest. So eventually, so what happens is slowly, see, it's like you are moving in that direction and you are constantly being pushed in that direction, let's say, right? Let's suppose you are going east and then you are constantly being pushed north. Then what happens? Slowly, after one step, you are turning a little bit. Another step, you are turning a little bit. Another step, you are turning even more and more and more and more. And eventually, you're going to be going to the north, even if you are not at rest. But yes, if it was at rest, it would start in that direction. And even it comes to the rest, it would not, as long as it is in the field, it keeps experiencing force. It means it wouldn't be at rest. Okay, unless, let's say, there is a field and you grab a charge and you put that here. Okay, so it could be at rest at that point when you just releasing it. Once you release it in the field, it cannot be at the rest because force is acting in it. Okay, so after answering that question on the Zoom, here is this question here. So now see how these positive and negative charge in the uniform field behave, right? So if a positive charge, then it's gonna go like that. Hey, does that remind some sort of motion here? So let's say if I were to throw a rock on the ground horizontally, then what's gonna happen? It's gonna hit the ground. So for this positive charge, looks like negative is like a ground. So it's going something like that. Okay. And for the negative charge, it's kind of going towards the positive charge. So this is like a ground. Okay. So that's how the motion of charge in a field looks like. Just like motion of a rock in the gravitational field. It's the same thing, nothing different. So when we threw a rock in the air, the path looked like something like this. And we said, okay, that was projectile motion. Okay. So basically, this is also a projectile motion. This is also a projectile motion. Okay. So I said we're going to be, let's say using also the notebook LM as a tutor, right? As a tutor. Okay. Not as the thing that gives you answer. Okay. If you use that as the some sort of thing that gives you answer, then you're not going to be learning much. So keep that in mind. Okay. So I hope you got my notification. I sent you last evening, yesterday. Okay. If you did not, that notification or the announcement is here. Oh, I was in the different screen, huh? That notification is in the announcement section. When I post it, it sends in the mailbox as well. Okay. So hopefully you did the Qualtrics, that survey. If you did not, I already closed it because I want student to do this before we start using the notebook LM. So we'll redo that after we use it. Maybe after first midterm or second midterm, I'll bring that up. Okay. And what do you think about it? So here it says download the materials from Canvas and then sign into trial notebook LM. So there is paid version and there is trial. So we are using trial. For us, trial is good enough. Okay. And it will allow you to upload the source file, it says. So for example, let's say, where is Canvas? So where are the files? How many of you downloaded and let's say, look at the notebook LM? So if we go to the files, so you see there is this class notes. So I am in the process of preparing them. So all of them are not ready. So every week I'll be adding them. So once they gets ready, once they are added here, you can download from them here. So for example, you can do and download like this, right? So it's going to download in your computer. So you download them. But more importantly, this is what I have. Okay. So basically, yeah, looks like these are the same notes up to magnetism draft I had. So I have posted those drafts here in our book. Okay. So I split the PDF version of our book into different sections so that the notebook LM allows you to upload it. Otherwise, if it's too big a PDF file, it will not allow you to upload it. So if you haven't done already, you want to download this in your computer. And once you have downloaded that, go to the Google. And by the way, in that notification, there was this video as well, which I actually, use that podcast I created with my script and dubbed it on the screen recording. It's not perfect, but it works. When I was trying to make that video, my heating system in the home was running and microphone was picking that sound. Okay. So I decided to do that. But anyway, so this is the address, notebooklmgoogle.com. And of course, you can just search for notebook LM and you can get there. And first time you go there, when you click that try notebook LM, you'll see this window here, this kind of window. Okay, just going to show you this kind of window. So that allows you to upload the file. Okay, that allows you to upload the file. So the files could be PDF, that's what I have done. But you can also upload your own file and could be text, or it can be also podcast, for example, right? It can also upload the audio file. And more importantly, you can also copy and paste the link of the website. And you can also copy and paste the link from YouTube. So for example, if you do that, it's going to allow you to paste the YouTube link. And it's not, so what it does is, so for example, let's suppose you missed the class or somehow you want to review this class. And I know watching this for 2 hours, it's gonna be painful watching this video, right? I know that. Watching a movie 1.5 hours gets sometimes, boring. And this is physics class. Try to totally understand. But what you can do is now with this tool. So this is the first class we had. So now, for example, we can get the shareable link here and copy this. Once we copy that, we can paste that one over here. Okay? And then insert. So if it has a transcript, then it's going to work. Looks like this one has transcript. So now, once I click on this one, okay. Oh, why this video not available? Okay, so it basically, shows you transcript. So now if you want to learn about electrostatics, you can just click on the electrostatic portion and it's going to show you all about the electrostatics. Types of charges. There are two types of electric charges, positive and negative. These charges are fundamental property of matter and so on, right? So that you can do. Or with that, you can also ask it to, let's say, make a podcast. Let's say you want to just listen it. Then you can do customize and say what you want that podcast to focus on. Remember, this is only for the first class. In the first class, what did we learn? Types of charges and method of charging. Okay. So let's say, you say, okay, focus on types of charges. Let's do something like this. Types of charges and method of charging. And then say generate. And it's going to take a little bit time, but eventually they're going to be, audio. And you can stop that audio while listening and ask question when it's talking about, okay, let's say you are talking about method of charging by induction. Can you make it more clear or explain it a bit better? Okay. So, those people who you listen talking, they're going to pause and take your question and then answer. So it is still on the trial. But generating that audio conversation going to take a few, like 10, 12 minutes, okay? And so I'm not going to wait for that. But here, it's like now you're on Chat GPT where you can ask question related to this class, okay? How do I charge a conductor? Oh, I don't know how to type. Using induction method, let's say. And then you do that, and it's going to give you all the detail. So first step is polarization when you bring the positively charged object. And then second, you provide the path, means you ground it. And then disconnect the path, disconnect the wire. And then you remove the charged object, the charged rod you brought. And then what happens? The conductor is left with the opposite kind of charge, right? So that's what we learned. That's what we talked about. And this basically summarizes that process here. But more importantly, So I have just this, class number 1, we did not do much problem on that. Rather, I'm gonna go something else that has more source. So I have a bit more source here. So you can say, okay, something like this. So if you go to someone to learn physics, let's say, something about something, what do? You ask question, right? You don't bring a question there and say, okay, can you give me the answer of this problem? Probably that's not how you go to the tutor, right? When you go to a tutor, what you do is you ask that tutor, okay, I am trying to solve a problem, something like related to, let's say, uh, finding force on a charge. So I have a charge and I'm trying to find force on that charge because of the other two charges, right? Can you help me how to figure that out? So that's how you want to learn. That's how you want to get help, okay? So that's how you want to formulate question here, okay? That's how I want you to use it. So for example, yes, of course, you can have your own prompt, but here what I'm writing is, how do I proceed, yeah, on finding, let's say, net force on a charge due to two other charges. And see that that charge could be positive or negative, and other two charges could be positive or negative. No matter what they are, the process is going to be same, right? Charge due to two other charges. And now we can have these three charges, and we learn two types of configuration, right? One where all the charges are along a line, and another case they were in triangle. So let's say they are all in a straight line, okay? Other charges all along a straight line. I haven't tried it, but I think you can also ask, okay, can you guide me step by step? Can you guide me through solving a a problem, something like this? Make your prompt and ask for the guidance. They may just give you some sort of help over there. But I noticed that ChatGPT has the plugin from Khan Academy called Tutor Me. So basically, that also guides you. Okay. So now, see here, it tells you how to do it. So read the question and identify the charges and their positions, right? So that's what it says. Note the magnitude and sign of the charges, positive, negative, and how much value it has, how many microcoulomb. See, all the details it gives you. Calculate the individual forces using this formula. See, it gives you all, it guides you better than any tutor. Okay? And then determine the direction of each force and how the like charges repel, opposite charges attract helps you determine that, right? And then add forces vectorially, and it also tells you how, and even it kind of looks like it gives you an example. Okay. And then ask you, hey, go ahead and do this problem. See? So that's how I want you to use it. Okay. Okay, with that said, now let's do this problem here. So this is a relatively long problem, okay? So it says an electron, so that means we are talking about this negative charge, not the positive, okay? Just to explain, I showed you both, but Here, there is no positive charge, just the negative charge. So that's how it's going to look like. Horizontally into a uniform electric field with an initial velocity. So let's say in that direction. So you are pushing in that direction. And let's say that is positive y and this is positive x, right? It's like a projectile problem. So what happens is that initially, so, oh, it says horizontally. So which one is our horizontal? Maybe I should have, turn this one 90-degree on the slide. But anyway, so horizontally does not matter. Vertical, you can say, okay, this direction is horizontal. So let's say this. Usually we say, okay, that is the x and that is y. So let's do that, okay? So it's the axis. So now what happens is Bix is that much. Velocity in the x direction, okay? Directed vertically upward means along the y direction and has a magnitude of that. So electric field is in y direction and 500 Newton per Coulomb. So how did I know this is in y direction? Because it was launched horizontally and it says field is vertically. Okay, so that means horizontal and vertical, they have 90-degree. So if this is in x direction, this is going to be in y direction. Okay, so if this is horizontal, then this is going to be vertical, right? So that's that. And a screen is placed at 0.1 meters away from the point where the electron enters the field. Okay, so now what's happening is electron enters the field somewhere here, and the screen is at 0.1 meter, right? So that means from the point where the electrons enters the field. Now it says calculate the time it takes. So that means it's going to be a displacement of the electron. Is it in x direction or y direction? Calculate the time it takes for the electron to reach the screen. Assume the effect of gravity is negligible because mass is so small for the electron. Gravitational force we can neglect. Okay. So we are given a displacement. Okay. So now what happens is this field is vertical, just like gravitational field is vertical. And if something is moving horizontal, the vertical field does not have effect in horizontal motion, okay? So we can say, okay, so which way we said was x? This one as a x. So delta x is 0.1 meter. So it's asking us to find time. For that is how much in part A. So now using the equation, which equation we should be using? So displacement is given, right? Initial velocity is given, and we are interested in time. So final velocity we don't know. So looks like we should be using this equation here. Delta x is Vix plus half Ax and delta t square. There should be delta t here as well. Okay. So acceleration in x direction is 0. See, Ax is 0 because field is vertical. Okay. So that tells us that time interval going to be just delta x divided by Bix. And we know both of these. Okay. Now in part B, what is it asking? Calculate the vertical deflection of the electron when it hits the screen. So delta y is what? Okay. So now in the y direction, it is accelerating. And what is the acceleration? Force in y direction, time divided by the mass of the electron. And force, being electric force, we have this QE over M. So that's what it goes. And if it is electron, then you have mass of an electron, and this is E. The value of that one is E, and it is given by this. So now we have acceleration, and we know time. Time is same in projectile motion, right? Delta T is whatever you get from A. So that means now delta Y is again the same formula, but this time acceleration is not zero, but this is in Y direction. Oh, delta Y is VIY times time interval plus half AY times time interval squared, okay? Oh, I'm just realizing it's already 53. Sorry about keeping you late, okay? So now you know everything here. So this VIY going to be 0 because it was thrown in the x direction. So that means VIY is 0. So we know everything means you should be able to calculate that, okay? So it is just using kinematic equation in x and y direction. That's all it is. Only new thing is now you are getting acceleration using the field. That's it, charge and field. That's it, okay? Yeah, so I did not quite finish all the slides because I started showing you how to use Notebook LM, okay? So we'll just leave it here and we'll pick it up from, this next slide, next class, and I'm gonna move forward. Again, sorry for, being a little late.